Welcome to lecture number 5 of Civ 360. Where are we at this point of our class? So we have this hierarchy between displacement, strain, stress, and force. And so far, we have focused on the following. We have representations for the stress. There are two types. We have a sigma and a tau, and they are both generated at this point, assuming that the stresses are uniform, and the most likely application of that would be the axial bar. And we can take the bulk force divided by the bulk area as a general rule. Now, there's clear exceptions to that. For example, stress on an inclined plane, we've got to do some adjustment. But it typically implies then that the stress doesn't vary over the cut area. And that's what we've looked at so far. So some fairly simple systems. But the sentence that we also want to have in mind is that we integrate stress to get force. So we integrate sigma to get F, and this is over the area. Then we also focused on this. We have the link now between displacement and strain. So we've looked at some pretty simple problems so far, the stretched rubber band, the sheared plate, and so on. And it basically says if you give us the deformed shape, then we can give you some measures now of the normal strain and also the shear strain. Now there's a little bit of work to do. We've got some more broad applications of these measures to kind of investigate. But as a rule then, these have either a delta length over length if the strain is uniform, and then also the gamma would be the delta theta. I'll write it like that. So in this case, the normal strain, change in length per length, shear strain, change in the angle. They are both dimensionless quantities, but we have that basic idea. And now, if we were to look at a sentence for this, let me draw it like that, then we would say we integrate strain over length to get displacement. So I'll abbreviate this. We integrate strain over the length to get the displacement. So they're both integrating steps. Going this way to this way, we integrate over length. Going from this to this, we integrate over the area. Well, I've got some good news now, because our next topic is going to be the relationship between stress and strain. So we'll write it like this: stress-strain laws. There are a number of other labels that are frequently slapped on this particular relationship. Some people call this as double bullet these things. Some people use just a phrase like we wrote out. They'll say it is the stress-strain law. That's probably the most common. And law, whenever you see a word like that, that typically means some sort of empirically derived formula, which is what we're going to have. This is something that's measured in the lab. So the stress-strain law or the stress-strain relationship, any of those phrasings is okay. Another phrasing that's typically used is simply, people will call it the material law. In other words, how does the material respond? What's the relationship between stress and strain in that particular material? A more complicated word, and one that is commonly used, is constitutive. One of my old continuum mechanics teachers would always call this constitutive, but most people say constitutive relations. And all of these mean the same thing. And we'll try to sprinkle in use of all of those as we work our way through the class so you can get kind of used to them. Before we dive into what those relationships are going to be, though, what we want to start with is narrowing down our class of solid. So let us narrow things down. And the reason that we want to do that, I'll put a colon there, we want to look at the simplest possible solids. So I'll say the simplest behavior. Because there are a number of solids or solid types of systems that we just don't yet have the academic experience to explore quite yet. For example, I think the first day of class I mentioned a clothing. So that would be a low-density fibrous composite. That's going to have a different sort of relationship between stress and strain of steel, which has a different relationship of your pencil eraser, which has a different relationship than, say, mud. So we want to focus on the following sorts of solids. So we're going to say that we assume our solids are, and we're going to have 4 words that describe these. The first is linear. Now we say a solid is linear. That's really kind of a shorthand. It means that the relationship between stress and strain is linear. And you have already seen in your educational background what the word linear means. It's got a number of applications. You probably learned it first in math. In fact, let's talk about that. In the math field, you said something like a function f is linear. If you have f of alpha x plus beta y is equal to, where alpha and beta are scalars and x and y are forcing functions, then if it's linear, then you can write alpha times f of x plus beta times f of y. In other words, you can kind of split things up. In practice, what that means is that if your structural response or your solid response is linear, it means this. If you've got 2 forcing functions, let's say one is 10 and one is 20. Now, in our problem then, alpha would be equal to the factor of 10. Beta would be equal to the factor of 20. X represents this loading, a load of 1 at the midspan, and y is the function that represents this. So what that means is this is f. In other words, find out what, let's say that f measured the displacement right here. So that would be the f. Find out the displacement at the end because of a 10-pound load at the middle and a 20-pound load at the right-hand end. And if it's linear response, then you can get that by taking that loading and multiplying it by 10. I should say get the displacement there, multiply it by 10, then take the displacement here, multiply it by 20, and you'll get the same thing. Now, for our purposes, it means that if a stress of 10 gives an epsilon of 0.001, then that means if it's linear, a stress of 20 is going to double the strain, 0.002. In other words, it goes up as a constant of proportionality. So when we say that our response is linear, it just means that we can upscale by some particular scaling factor to get the exact same result. So that is our response. Our solid is going to have linear response. The second word that we use is the word elastic. This one's easier to define. Elastic means that you take a solid, you load it, it deforms, you take the load off, and it goes back to its original configuration. So we say that the solid returns to its original shape when the load is removed. So your chair that you're sitting in right now, when you sit down in it, it deforms. When you get back up, it's going to go back to its undeformed configuration. A piece of chewing gum, if you take it and you bend it, you take the ends, and you make the ends touch, then you let it go, it's not going to go back to its original state. So that would be an inelastic or anelastic. So all of our response is going to be elastic. It is going to return back to its original shape. And again, that's the simplest possible type of constitutive law. The third word that we're going to use to describe this is going to be homogeneous. And that means that the stress-strain relation is the same everywhere spatially inside of our solid. We get the same relationship between stress and strain at all locations in the solid. Now, there will be some minor exceptions to this because we will probably look at problems that are maybe made of more than one material. But if we do that, we'll basically say this is a composite type of solid. But what we are doing is, so for example, if I have a bar that is made of half of steel, half of aluminum, that would be an inhomogeneous bar or a composite bar. But inside the steel, it's the same at this point, this point, this point, and so on. The aluminum has the same properties here, 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 and so on. So homogeneous just basically means it's going to be the same throughout at all spatial locations. So again, when you think of the word homogeneous, think of location in space. The fourth and final phrase that we're going to use to describe our material and our stress-strain law is isotropic, which means same direction. So that means that we have the same relationship between stress and strain in all directions. Period. What that means is if we have a blob of material, it means that I can go to one point and I go this way and I cut out a little test bar. Then I cut out another little test bar going this way, and then another little test bar going this way. I cut out 3 bars, I get exactly the same relationship. So 3 bars in any direction. So again, the link that you need to memorize is when you think isotropic, you think direction. So metals, plastics, I'll say glass, plastics, etc. All of those have isotropic behavior. Material like wood, fiber reinforced composites, reinforced concrete, those would be anisotropic. We're not going to consider those except in very special circumstances. So the isotropic is linked with direction. Well, I'm really going over. I owe you guys a couple of shorties here, but that's going to punch us out then, those 4 keywords that we have for our first part of today's lecture.